Alright, today we're talking about Chapter 11, Section 7, Events Involving and Conditional Probability. Okay, so today we're just doing a simple probability problems that we have been doing. It's just now we're just kind of adding on to them. What is the probability of this happening and this happening? And that's it. And I think I've said and a lot now. But the arithmetic behind it is you're just multiplying. So let's go ahead and put this independent events right here. Alrighty, so the first part of the text up here talks about moving to Miami, but we don't like hurricanes, which makes sense. I don't really like hurricanes, um, and I think we revisit it in example 2 or 3. But for now, we don't really need the context of it. Instead, let's talk about two definitions here. Independent events. So an independent event, two events are independent events if the occurrence of either of them has no effect on the probability of the other. Okay, so given the example in the text is flipping a coin, right? If you flip a coin and it gets heads, well, the next flip, the heads from the previous flip doesn't matter. The next flip is brand new. Okay, so independent events is if the if sorry if the occurrence of either of them has no effect on probability of the other. We have and probabilities with independent events. So if A and B are independent events, then again this we read this as the probability of A and B is simply going to be the probability of A times the probability of B. Okay, and so that's just basically going to be the the major part of this section. We're just multiplying probabilities. So let's start with a roulette wheel. Excuse me. All right, so I'm just gonna snip this roulette wheel just to kind of show you what it looks like. But you've probably seen a roulette wheel in movies or TV shows or something. But anyways, so Figure 12 shows a U.S. roulette wheel that has 38 numbered slots, numbered 1 through 36. It has a 0 and it has a double 0. Of the 38 compartments, 18 are black, 18 are red, and 2 are green. Now, the 2 being green, that is the house. Okay, so basically, just to kind of give you a background on this, when you play roulette, you generally, for the most part, think you have a 50-50 shot, and I mean, I wouldn't say you kind of do. Let me get my calculator out quick, because I don't think this is part of the problem. So 18 divided by 38. You generally have a 47% chance of being correct on a U.S. Roulette wheel. And that's because, well, you hear the house always wins, and again through thousands of roulette playing, uh, your chance of winning is only 47%, and the house's chance of winning would be 53%. So that's why that's why the house always wins, and that's why we have those two green areas. So a play has a dealer spin the wheel and a small ball in the opposite direction. As the ball slows to a stop, it can land with equal probability on any of the 138 numbered slots. So find the probability of red occurring on 2 consecutive plays. All right. So um, I'll talk about gamer's fallacy here in a second. So what are the odds that we land on red on 2 consecutive plays? So if we go back and look at our formula, which we don't necessarily need to go back and look at it, but if you recall, it's uh, probability of A. The probability of A and B occurring is just simply the probability of A times the probability of B. Okay, so we're wanting to know what are the odds that we land on red uh, 2 straight times, right? Yeah, okay. So what are probabilities we land on red 2 straight times? Well, what's the probability of we landing on red the first time? Well, in the text it says there are 18 red. Okay, so there are 18 red, and then there are 38 different compartments. Okay, so that's the probability of us landing on red the first time. And of course we can, and we will, I guess, reduce that down. But what's the probability of it landing on red the second time? Well, it's the same probability. Okay, because as of right now, these are not independent events. Okay, so what is 18 over 38 times 18 over 38? Well, we can reduce this down to 9 over 19 times 9 over 19, and we get what? 81 and 361. So 81 over 361. All right, so there is a 81, 361, so 81 divided by 361. There is a 22.4% chance that this happens. Okay, 0.224. So there's a 22% chance that we land on red twice in a row. Now, real quickly, I'm gonna give you a just kind of gambler's fallacy here, and I think it's what it's called. I don't know, but I know my friends, and I should say my friends, but everybody. So if you flip a coin, okay, or just use a roulette wheel. Um, if you land on red, let's say 6 straight times, right? People will start to think, okay, well, it has to land on black sooner or later. But that's not the case at all. On every single roll, it's 47%, 47%, and I guess 6% for the green ones. So that's kind of a gambler's fallacy saying, okay, so this has happened 6 straight times. The seventh one has got to be black. And then guess what? You put a lot of money on it, it's red again, and you lose a lot of money. So that's just a gambler's fallacy. And I believe that's what it's called. Okay, so next up we're going to have a large family. Okay, so alrighty, so well, I guess we should bring the picture since it references it. Alright, I don't know why we need the picture, I guess, but here it is. Okay, so the picture in the margin shows a family that had 9 girls in a row. Find the probability of this occurrence. Okay, so the probability of having 9 girls in a row. As far as we know, and there might be some science out there, whatever. There's a 50-50 chance you're going to have a boy or a girl. So if we were to say, what is the probability of having 9 girls in a row? Well, you would just say, okay, so 1/2, all right, times 1/2 times 1/2, and you would do this 9 times. Dot 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 1/2. You do this 9 times. Okay, but we know another way to write this, don't we? We know we can rewrite this as 1/2 raised to the ninth power, right? Because something multiplied by itself, well, that's just an exponent, right? So 1/2 raised to the ninth power is 9. It's 250, 2 to 9, 250. I think I forget my 2's. 2 raised to the ninth. It's 512. Okay, so yeah, there's a 1 in 512 chance of having 9 girls, or in other words, that would be 1 divided by 512. That is a 0.002002% chance. So it is 0.2% chance of occurring. And while we're on this particular example, this can be seen. Let's say it wants to be seen, but the exponent method that you see here, you could use it like in basketball, right? What are the odds somebody that shoots 70%? Okay, so let's just go ahead and do that. What are the odds that somebody shoots 70% from the free throw line? What are the odds that they can make 10 straight? Okay, so you would just say 0.7 raised to the 10th power, and that's roughly about a 2.8% chance. So it's 0.028. Okay. And of course, that you can do this with all sorts of problems like that, but um, the basketball problem specifically will be helpful. All right, so example 3 is going to revisit the hurricane example. Well, the hurricane problem, I guess, from the text at the very beginning. But like I said, there's not much context that really needs to be here. Alrighty, so if the probability that South Florida will be hit by a hurricane in a single year is 5/19, what is the probability that South Florida will be hit by a hurricane in 3 consecutive years? Okay, well, what's the probability it gets hit in 3 consecutive years? Well, you would just say 5/19. You can do times 5/19 times 5/19, but we know we can just rewrite this as 5/19 cubed. Okay, and 5/19 cubed is going to be 125. I'm having to do this separately because otherwise my calculator will go ahead and do the problem by itself. There's nothing wrong with it. I just want to show the steps though. Over 6859. Okay, and we know that this in percentage will be 125 divided by 6859. About, oh, that's not, it's pretty low, 0.018 percent chance of occurring. Okay, so about almost a 2% chance that South Florida will get hit by a hurricane in 3 consecutive years. Funny thing, while I snip this, I moved to Florida a couple years ago, and up until that point, Florida, mainland Florida, I guess Florida Keys had, but mainland Florida had not been hit by a hurricane in like 14 years or something like that. And then the year I moved there, they get hit by 2, and then next year they get hit by another one. And it's just the way it goes. Alrighty, so B reads, what is the probability that South Florida will not be hit by a hurricane in the next 10 years? Okay, so what is the probability that it will not be hit? Well, if we want to figure that out, well, looking at the probability that it gets hit is 5/19, right? 5/19. So that means that the probability of it not being hit is 14/19, right? And then of course it says in the next 10 years, so you put 14/19, and you just raise that to the 10th power. And that's going to be 14 divided by 19 raised to the 10th. It's going to be 0.047. Okay, so there's almost a 5% chance that it will not get hit by a hurricane in the next 10 years. And I guess I don't like all that dead space. Let's just move this down a little bit. There we go. All right, so the probability of an event happening at least once. So the probability of an event happening at least once, well, it's just going to be 1 minus the probability that an event does not happen. So, hang on. Okay, so the arithmetic behind that, or just kind of explain this. The probability of an event happening once is 1 minus the probability of an event not happening. So just think about, well, let's think about the free throws. Okay, what is the probability of our 70% free throw shooter not? That's not a good one. Let's just actually go to the next example. Pretty sure that'll help out. Well, not necessarily. Okay, so let's look at. Oh, I'm sorry, guys. I totally forgot. This is actually kind of at the tail end of the previous problem, and this isn't part of the problem, but this is just kind of an add-on that I was going to try and go over, but I forgot about it. But we're here now. So the probability of an event happening at least once. So again, that's just the probability of an event happening at least once is equal to 1 minus the probability event does not happen. So again, this is piggybacking off of the previous example about hurricanes. And it reads, what is the probability of that South Florida will be hit by a hurricane at least once in the next 10 years? Okay, well, we did the arithmetic, right? B was a probability that South Florida will not be hit by a hurricane. Okay, well, we want to figure out now, wait for that to go away. We want to figure out now what is the probability that it will be hit by a hurricane at least once. So using the formula up here, and again, this is just kind of I dare say it, common sense here. Um, well, if the probability of no hurricanes for 10 years is 4.7%, well then what is the probability of at least one hurricane? Well, it's just going to be 1 minus that probability. And of course that would be 0.953. So hopefully that wasn't too confusing and I didn't skim over that uh, too fast. All right, so next up we're going to have dependent events and we're going to have and probabilities. So dependent events, well, let's just snip it real quick. I think we can share a page here. Excuse me. All right, so some more definitions here. Two events are dependent events if the occurrence of one of them has an effect on the probability of the other. So up to now, in our examples, uh, the probability of something happening has no effect on the second one, right? Like the roulette wheel. Getting red on one roll has no effect on the second roll. But now we're going to talk about dependent events where one of them does have an effect. And then breaking this down to our probability and probabilities with dependent events. If A and B are dependent events, then the probability of A and B is going to be equal to the probability of A times the probability of B given that A has occurred. So again, it's simply multiplication, but now it's not going to be as easy as just saying, well, I mean these two. It's not as easy saying 5 over 19 raised to the third power or 14 over 19 raised to the 10th power. Instead, we're going to be kind of reducing the total amount. And we've done stuff like similar to this before. So example 4 reads, good news, you want a free trip to Madrid and can take 2 people with you, all expenses paid. Bad news, 10 of your cousins have appeared out of nowhere and are begging you to take them. So you're going to write each cousin's name on a card, place the card in a hat, and select one name. Then you select a second name without replacing the first card. If 3 of your 10 cousins speak Spanish, find the probability of selecting 2 Spanish-speaking cousins. Now, again, I feel like we've done this, or at least something very, very similar to this before. Maybe it was another class, I don't know. But we want to figure out if 3 of my cousins speak English, find the probability of selecting 2 Spanish-speaking cousins. So I've got 3 out of my 10 speak Spanish. What's the probability of selecting 2 Spanish-speaking cousins? Again, I'm pulling their names out of a hat here. Okay, so on my first pull, I have, all right, so on my first pull, I have a 3 in 10 chance of pulling a Spanish-speaking cousin. Okay, on my second pull, well, looks like it's a P. On my on my second pull, okay, I don't have a 3 in 10 chance anymore. Instead, I have a 2 in 9, right? Because my first pull, I had 10 options to choose from, and 3 of them were Spanish speaking. Well, I take them both out. I now only have 9 cousins to choose from, and 2 of them that are Spanish speaking. So it just becomes this arithmetic here, which is going to be 6 over 90. 6 over 90, which 3 goes into both. Actually, 6 goes into both. So it's going to be 1 over 15, or in other words, 1 divided by 15. 0.606. We'll just stop at 7. Okay. So again, kind of same thing, but now we're taking out that selection, right? By taking out that selection rather, right? Again, we call those dependent events. Alrighty, so more of the same here. Alrighty, so 3 people are randomly selected, 1 person at a time, from 5 freshmen, 2 sophomore, and 4 juniors. Find the probability that the first 2 people selected are freshmen and the third is a junior. Okay, so the first 2, we're going to find the probability that the first 2 are freshmen. So how many total people are there? There's 5 freshmen, so 5, 7, there's 11 people here. Okay, well the first pool, the first selection, there is a 5/11th chance of us pulling a freshman. The second pool, right? Did I do it like that? Yeah, good. The second pool, again, I now only have 4 freshmen out of 10 possible students. Okay. And then my third pool, right? I'm looking for the third being a junior. Okay. Well, how many juniors are there? Well, there are 4 juniors. And how many students are left? Well, I'm going down one each time because I'm pulling their names out, right? So there's going to be 9. So this is just going to be 20, 80 over 1100. So 80 over 1100, which is going to be 0.7, 0.72072. We'll just round out to 3. Okay. All right. So that's the probability of us pulling 2 freshmen and 1 junior, and that's roughly 7%. So a little over 7%. All right. So next up, we're going to talk about conditional probability. Okay. I guess in a minute. Okay, so there we go. Conditional probability. So conditional probability, again, are just more probability problems here. Now we're going to have conditions, essentially. So, well, that's the name, conditional probability. We have seen that for any 2 dependent events A and B, we say that the probability of A and B is equal to the probability of A times the probability of B given that A occurs. So basically, it's just, well, the B, in order for the second probability to happen, A must happen. One moment. Alrighty, so this is written in this form here. So the probability of B given that A occurs is called conditional probability, denoted by our notation here. The probability of B with our line meaning given A happens. Okay, and again, that's just reiterated here in the sandy box. And again, this concept isn't anything hard compared to what we have been doing. It's pretty much in line with what we have been doing. Okay, so this particular problem reads, a letter is randomly selected from the letters in the English alphabet. Okay, so find the probability of selecting a vowel given that the outcome is a letter that precedes H. Okay, so how many letters precede H? So A, B, C, D, E, F, G. There are 7 letters that precede the letter H. Okay, so there are 7 probabilities here. Okay, well, how many letters in those 7 are vowels? Well, A, E, I, O, U, so A and then E, those are the only 2 options. And honestly, this needs to be put right here, smack dab in the middle. All right, 2/7. And I don't know if I should do this, but 2 divided by 7 is 0.29. Okay. So if you randomly select a letter from the English alphabet and we find a probability of selecting a vowel in the first 7 letters, well, there's a 29% chance that will happen. And I mean, that's conditional probability. Okay, so back to our 52 card deck. So hopefully by now we are very familiar with all the cards in a deck. So A reads, you are dealt 1 card from a 52 card deck. Okay. So find the probability of getting a heart given that the card you were dealt is a red card. Okay, so if you recall, and actually let's actually go ahead and pull the pictures for this one. I feel like they help. Well, at least a picture for A. So it says find the probability of getting a heart given that the card you were dealt is a red card. Okay, well, we know that there are 4 suits in a standard 52 card deck, and in those 52 cards we have 13 diamonds, 13 hearts. We also have 13 spades and 13 clubs. Okay, but that doesn't really matter because we're pulling a red card. So find the probability of getting a heart given that the card you were dealt is red. So if I have a red card, what is the probability that of those red cards, it is the one I got is a heart? Okay, well, looking here, there are 26 possible choices, and let's make this as A. There are 26 possible choices of getting a red card. Well, there are 13 possible choices of getting a heart of those red cards. Okay, so this is pretty easy arithmetic here, just simply 1/2. So if you're dealt a red card, the probability that it is a heart is exactly 1/2. I'm pretty sure we can also put B on this page as well. So let's just go ahead and split this down the middle, kinda, and put B here. All right, that B doesn't look any better. Whatever. Okay, so find the probability of getting a red card given that the card you were dealt is a heart. Okay, well, if I'm dealt a heart, all the hearts are red anyways. All right, so what is the probability of getting a red card? Well, that's just going to be 100%. Okay, because again, every heart is red, and so that's just no, it's a silly example. It is what it is though. Alrighty, so I think this is the last one for today. Alright, so example 8 reads, when women turn 40, their gynecologists typically remind them that it is time to undergo mammography, I don't know, screening for breast cancer. The data in Table 7 are based on 100,000 U.S. women ages 40 to 49 who participated in the screening. So we have our chart here, and A reads, assuming that these numbers are representative of all U.S. women ages 40 to 49, find the probability that a woman in this age range A has a positive mammogram, given that she does not have breast cancer. So let's go ahead and look at this. So what is the probability that she has a positive mammogram? So we look over here. Here's a positive mammogram row. All right, and it says given that she does not have breast cancer. So 6944. Okay, so 6944 is going to be the top number because we're wanting to know the odds of having no breast cancer and a positive mammogram. So 99,200 are the ones with no breast cancer. 99,200. And again, I'm looking right here. So I'm looking at the positive mammogram that do not have breast cancer divided by the total amount of mammograms that do not have breast cancer. So this is going to be 6944 divided by 99200. Oh, it's 7%. That's nice and round. So 0.07. So there's a 7% chance that a woman will have a positive mammogram and does not have breast cancer. That's a pretty high, what am I trying to say? It's a pretty high false test there. Anyways, so then B was the probability that the woman in this age range does not have breast cancer, given that she has a positive mammogram. Okay, so what's the probability that she does not have breast cancer? So what we're going to do is we're going to look at, and it says given she had a positive mammogram, so we're going to look at this first, this top row. What does not have breast cancer? So we're going to use the same number, 6944. Divided by, well, again, given that she has a positive mammogram, and how many positive mammograms were there? Well, there were 7,664. 664. So that's 6944 divided by 7664. There is a almost 91% chance, so 0.91. Okay, so there's a 91% chance that a woman in this age range does not have breast cancer, given that she has a positive mammogram. Right, so again, that's just conditional probabilities, and like I said, I think that about sums it up. Yes. Okay, so that does conclude today's lecture.